students. Today we're going to discuss about the simple stress and strain. So before this video, we have discussed in the first video we have discussed about the properties of the material. Then what is difference between the engineering mechanics and strength of material? Types of stresses we have discussed, that compressive stress, tensile stress, and uh, shear stress. Then strain also we have discussed. There are three types of strain, that is compressive strain, tensile strain, and the shear strain. And after that we have discussed about the Hooke's law. Okay, so in this video we're going to discuss about the Hooke's law. Hooke's law is applicable for material within the elastic limit, or in short we can write stress is directly proportional to the strain, or stress is equal to a constant into the strain. In the case of tensile and compressive, this constant is denoted by a symbol capital E and is known as the Young's modulus of the elasticity. Thus, sigma is equal to that capital E into small e. Capital E is be the Young's modulus and small e be the strain, and is mathematically form of the Hooke's law. E is the property of the material and may have a fairly constant value in some cases, but it can also be depends upon the stress and may be different in compression and tension. Note that sigma is equal to E capital Young's modulus into the strain, and since E is a non-dimensional, the unit of E should be the same as that of the sigma. Thus, E can be expressed in Newton per mm square, or it is also expressed in Pascal, megapascal, gigapascal, etc. So E is nothing but stress upon Young's modulus. E means strain is equal to stress upon Young's modulus, or mathematically we can, you know that sigma is nothing but P upon A. So sigma is replaced by P by A, then the strain becomes P upon A. But you know that E, that is the strain, is nothing but change in length upon original length. By substituting the values of delta L by L in this first equation, you will get delta L by L is equal to P upon A, or that delta L is equal to PL upon A. So this relation is very important while you are solving the numericals. Then the next part of this unit is modulus of rigidity. In the case of shear stress and shear strain, a similar relation exists, that is that of Young's modulus. The shear stress is directly proportional to the shear strain within the elastic limit. Then mathematically we can write a shear stress is directly proportional to the shear strain, or tau is directly proportional to the phi. The tau is a shear stress and phi is a shear strain. Or shear stress is equal to constant, that constant is denoted by letter capital J, into phi. Phi is nothing but the shear strain. The constant in this case is known as a shear modulus or modulus of rigidity, and it is usually denoted by letter capital G, or sometimes it is also denoted by letter C or N, so that tau becomes, shear stress becomes G, that is modulus of rigidity into the shear strain. Idealized stress strain curve. Now, if a member is subject to tensile force, then, and if you try to plot a graph stress versus strain, then uh, when as the force going to be increased, so we'll get the straight line which is passing through the origin. This graph, a typical stress strain diagram for the Miles Lee, is as shown in figure. There are some important characteristics in this diagram that should be noted. The diagram is linear in the beginning and up to the point A, known as a proportional limit. So this up to this point A is known as a proportional limit. Then again, if you apply a force on this member, then we'll get the B point. It is known as a upper yield point. When again you try to apply the tensile force, then suddenly there is a fall in the force, and after that the bar is taking a force. So the lower, the C point is known as a lower yield point, and continuously there is an increase in the force, then there is a small increase in the force as compared to the this change. So change in length is large as compared to the external force. So this point is considered, point D is considered as a upper yield, ultimate stress point or ultimate load point, and finally the member will break if you are again increase the load. Then after that D there is a continuous fall in load, decrease in the load, but there is a continuous decrease in the length, increase in the length of the member. So finally the final the member finally get failed. That point is known as a E, and it is known as a breaking point or rupture point. So this diagram indicates the stress versus strain for different material. The first diagram, this diagram, when we try to draw the stress versus strain, we will get the straight line, but you will get the very less deformation, but we will get the very large force, and it is applicable for the brittle material. When a strong material which is not ductile, then you will get the stress strain diagram, this one, and this is idealized stress strain curve for the ductile material. You will get the straight line which is passing through the origin. Then this is upper yield point, lower yield point, ultimate, and this one is the breaking. So if you try to draw the stress versus strain diagram for the plastic material, then you will get the very large deformation with a very small increase in the load or stress. So this is the stress strain diagram for different material. Then materials are classified, that is elastic material, plastic material, elastoplastic material, and the ductile material. Already we have discussed this in the first video lecture. Let us take a simple example. A circular bar of 20 mm in diameter and 250 mm long is subjected to a force of 30 kN. Find the stress, strain, and elongation in the bar if the value of Young's modulus is 80 GPa. So first of all, you write down the given data. What is given? Diameter of the bar is given as a 25 mm, load is given as a 30 kN, and Young's modulus is given as a 80 GPa. What is required? In the statement of the problem, it is mentioned that stress, strain, and the elongation is to be required. First of all, you calculate the area of the bar. So bar is having circular, so we get the area is equal to pi by 4 d square. Subtracting the value of d, that is 25 mm. So we'll get the area of the bar is 490.87. Then we know that stress is nothing but P upon A. Then the P value is given as a 30 into 1000. Why this 1000 is multiplied to the 30? Because 30 is expressed in kilonewton here. So you convert this 30 into Newton. So we'll get the stress is equal to 61.12 Newton per mm square. Now Young's modulus is given at 80 GPa. So you convert this GPa into the megapascal by multiplying it 1000. So you'll get 80,000 MPa, or 80 into 10 raised to 3 Newton per mm square. Once we know the stress, then strain we can calculate, that stress upon Young's modulus. Substituting the value of stress as a 61.12 divided by 80 into 10 raised to 3, that is 80,000. We get the strain is equal to 7.64 into 10 raised to minus 4. Then elongation is nothing but stress into the strain into the original length. Strain already calculated, that is 7.64 into 10 raised to minus 4. Multiplying by the original length of the member is 200. So we'll get it as a 0.191 millimeter. That is the change in length. The next problem, the ratio of Young's modulus of elasticity of the two material is 2.85. Find the ratio of the stress and elongation in the two bars of the material if they are of the same length and the same area and subjected to the same force. Now what is given? Ratio of Young's modulus is given, that is 2.85. The same length and same area and subjected to the same force. This is mentioned in the statement of the problem. So required the ratio of the stress and elongation of the two bar. So first of all, you write down the stress formula. Stress is nothing but P upon E. So P is the load applied on the member and A be the cross-sectional area. Now load P and the area remains the same. The ratio of stress becomes 1. Then strain in the bar is equal to stress upon Young's modulus divided by the length. So strain in the bar is equal to sigma divided by E2 into L. So this is for the first member and this is for the second member. Length being the same, the ratio of elongation will be the same as the ratio. By substituting the values of E1 and E1, here you will get it as a E2. Ratio of elongation E1 upon E2, E1 upon E2, you substitute the value of E1 and E2, and by solving equation, finally you get 1 upon Young's modulus of the first material divided by Young's modulus of the second material. So this ratio will get it as a 0.35. The next problem, a bar of cross-section area 490.87 mm square elongated by 0.7 mm over a length of 650 mm when subjected to a tensile force of 12500 Newton. Find the Young's modulus of the elasticity of the material in the bar. What is given? Area of the member is given, length of the member is given, external force is given, and change in length is also given. So what is required? Young's modulus of elasticity is required, that capital E. So stress, we can easily calculate the stress, that is P upon A. Substituting the value of P and A, will get that stress is equal to 25.46 Newton per mm square. Then strain is equal to stress upon Young's modulus. Stress is known 25.46 divided by the Young's modulus. Young's modulus is not known, so keep as it is, or we can write elongation is equal to Young's modulus into the original length. So by substituting the values of E in this equation, we'll get 25.46 L divided by the E. Elongation is given as a 0.7 millimeter. Therefore, 25.46 into 650 is the length divided by the Young's modulus is equal to 0.7. This value, all values are given. By solving this equation, we'll get the Young's modulus. Young's modulus is equal to, that is 23.64 into 10 raised to 3 Newton per mm square. Then we're going to discuss about the fourth example. A circular pipe of internal diameter 40 mm and thickness 3 mm is subjected to the force of 40 kN and the elongation was measured as a 0.8 millimeter. If the length of the pipe is 2.2 millimeter, find the value of Young's modulus and the elasticity and the stress in the pipe. So what is given? Diameter of the pipe is given, thickness is given, external diameter is given, external force is also given, change in length is given, original length is also given. So required Young's modulus of elasticity and the stress in the pipe. While you are solving the this example, you calculate the area of the pipe. So pipe is circular, so pi by 4 d square. Here the formula is written, pi by 4 external diameter square minus internal diameter square. So here we have calculated the internal diameter, that is internal diameter, if it is given as a 40, then 3 plus 3 6, so 46 becomes the external diameter. By substituting here, it is external diameter, this is internal diameter, so area you will get it as a 405.27 mm square. Stress in the pipe of the material is equal to sigma is equal to P by A. So substituting the value of P and A, will get as stress in the pipe is 98.69 Newton per mm square. The elongation of the pipe is given as a 0.8, length of the pipe is also 2.2 meter. Then strain is equal to change in length upon original length. Change in length is given, original length is also given. So we can easily calculate the strain by substituting this value. We know that Young's modulus is nothing but stress upon strain. So substituting the value of stress value and strain value in this equation, we will get that the Young's modulus is equal to 271.126 gigapascal, or 271 into 10 raised to 3 Newton per mm square. So this is the 4 example we have discussed today. In the next video, we're going to discuss the if the composite bar is subjected to the various forces and the cross-sectional area is also changes, then how to calculate the stresses in each member, that we're going to discuss in the next lecture. Thank you.